Good morning everyone and welcome to GTC 2022. I am Tariq Hamadou from NVIDIA. The title of our presentation today is Simulating and Optimizing Warehouse Operation based on Omniverse. But first and before we start, I would like to introduce my two co-presenters, Jeremy Jarrett and Bengt Abel.
Thank you, Tariq, and thank all of you for attending today. I'm Jeremy Jarrett with Kinetic Vision. We're an NVIDIA certified ISV and Elite SDP. In our previous GTC presentation, we shared with you how to build and deploy highly accurate computer vision AI applications using Omniverse and Metropolis. Today, we will share with you how to use the same frameworks to solve challenging problems within warehouse operations.
Thanks, Tariq. Thanks, Jeremy. Pleasure to be here with both of you today. My name is Bengt Abel. I'm a project manager of robotics and AI at KION Group. We integrate material handling solutions for retailers and manufacturers all over the world. My team and I working within the central technology organization, bringing these solutions to life.
Thank you, Jeremy. Thank you, Bengt. It's a pleasure to be with you. For our audience, here is the agenda today. First of all, Jeremy and Bengt will be talking about the problem we are addressing and the business implication. Then, Jeremy will join me to introduce the NVIDIA Accelerated AI platform. For our objective today, we will focus first on Omniverse and the importance of digital twins technology, from design and optimization to synthetic data generation. Then, we'll expand this section to talk about Metropolis and the enablement of deep learning applications. In section 3, Jeremy and Bengt will present and demonstrate how they are using NVIDIA Accelerated AI platform to simulate and optimize specific operation within a warehouse. And finally, we will share with you our conclusion and future work.
Let's define the problem. Let's talk about the supply chain. It encompasses all of the processes used to get products into the hands of consumers. It encompasses everything from obtaining raw materials to manufacturing, distribution, as well as the consumer experience. Defining and optimizing each process will lead to efficiency and driving quality across each step. Manufacturers and retailers are investing billions of dollars to optimize their supply chains by identifying critical gaps, then applying technology to achieve optimal results. Some of the most important parameters within a successful supply chain process are quality, accuracy, security, and throughput. Because of its interconnected nature, solving challenges in one part of the network can often create efficiencies downstream. The distribution center is an important part of the supply chain, where we marry manufactured product with the choices consumers make every day. On the input side, everybody knows how manual the receiving process is. Breaking down pallets, barcode scanning, and paper manifests that need to be rekeyed into the warehouse management system are just some of the challenges. At the other end, products have the potential to be picked incorrectly or in the wrong order, with storage and material handling challenges in between each step that can affect process quality. Combined, all of these have a negative impact on the throughput and in most situations lead to a decrease in customer satisfaction and higher operational costs.
Let's have a closer look into the fulfillment and distribution processes and where AVA can support each step. Here are some examples where we can support the workers with machine vision and edge AI. We start at the beginning, where the goods arrive. Here, the quality of the goods must be checked, the labels scanned, and the good receipt posted. The entire process is best done directly on the forklift truck. Once the goods arrived at the warehouse, it must be stored in the shelf. Today, the shelves are all the same size, and much of the warehouse volume is wasted. By automatically measuring the dimensions of the good, the volumes of the warehouse can be better utilized. Inventory means to record the current stock of goods. Today, this means manually counting all pallets and packages and a lot of paperwork. When picking the good, it's very important to grab the right products and send them to the right packing stations. This is very challenging, up to 50,000 different products in the warehouse. But it's not only important that the right products are picked, but also that they end up in the right number on the right pallet or in the right package. But the job is far from done once the goods have been put together correctly. Transport security to the next warehouse or production must also be ensured. Adding cameras and AI to the warehouse is very difficult. Fixed cameras on the conveyor belt must cope the high speeds of the products passing by them. Cameras on the forklift are all edge devices. They can't stream full videos directly to the servers and must process them locally. Therefore, reducing the size and optimization of networks for efficient edge processing is necessary. And the design of the 50,000 products change frequently.
Solving these challenges requires a new development standard. We've reached the speed limit of physical iteration within these complex supply networks, and with the acceleration of e-commerce, a digital-first approach is needed. Digital twins that model these supply chain systems and allow collaboration across many data sources are needed to scale new automation solutions and remove the bottlenecks of legacy systems. We will need to classify and detect damage in thousands of products, optimize our networks for more edge computing, and enhance the performance of existing material handling processes like depalletization, conveyors, and picking operations. We also can't afford to create one-off solutions for every installation. Digital twins will allow solutions to be developed that can cross domain gaps at different manufacturers and within different material handling systems. To enable the rapid development of solutions, we will start with NVIDIA AI frameworks with a focus on Omniverse and Metropolis.
First, let's talk about Omniverse. What is Omniverse? NVIDIA Omniverse is an easily extensible, open platform built for virtual collaboration and real-time, physically accurate simulation. Creators, designers, researchers, and engineers can connect major design tools, assets, and projects to collaborate and iterate in a shared virtual space. This platform eliminates the tedious import-export difficulties users are normally plagued with, and allows designers to work on incredibly large single source files from anywhere. One of the main characteristics and feature of Omniverse is the use of USD, an easily extensible open source 3D scene descriptions and file format developed by Pixar for content creation and interchange among different tools. Omniverse is being widely adopted, not only in the visual effect community, but also in architecture, design, robotics, manufacturing, and other disciplines. Let's now discuss briefly the different components of Omniverse. On the left, collaborators working on different software tools compose their part of the scene, whether it's modeling, building an environment, texture painting, lighting, or adding animation or effect. With Omniverse, they can now connect into the Omniverse nucleus with Omniverse connectors and work together seamlessly. In the center, we see the core of Omniverse, Omniverse nucleus. This is the database and collaboration engine that enables the interchange of 3D assets and scene descriptions. This platform has been built from the ground up to be physically based and integrated with the core NVIDIA technologies like physics, AI, and real-time ray and path tracing. Scenes built in Omniverse obey the laws of physics and are true to reality. Finally, on the right, viewer can portal in and out of Omniverse with workstations or laptops, and even teleport into Omniverse with virtual reality, or out with augmented reality. Anyone can view a scene on Omniverse by streaming RTX to their device. An important component within Omniverse is the connector. Connectors are what connects the designers and their applications to Omniverse Enterprise. Some connectors are built by NVIDIA, and many other connectors are built by the large number of ISVs we're working with. As you can see, There are two types of connectors. The bidirectional connector shares real-time updates between both the application and Omniverse in real time. Material conversions are supported as well. The unidirectional connector reflects the real-time updates in Omniverse, but updates to Omniverse are not shared back to the application. Now that we understand the basic of Omniverse and how it works, let's look at the entire platform and the different components. There are 5 key components to Omniverse. First, Omniverse Nucleus allows users to store, share, and collaborate on project data and provide the unique ability to collaborate live across multiple applications. Nucleus works on a local machine, on-prem, or in the cloud. Then, Omniverse Connect opens the portals that allow content creation tools to connect to the Omniverse platform and save USD and MDL content. Omniverse Kit is a powerful toolkit for developers to create own Omniverse application and extensions. Then we have Omniverse Simulation, powered by the core NVIDIA technologies that simulate the world, including physics, flow, blast, and rigid body dynamics. And finally, we have Omniverse RTX Renderer. It's an advanced multi-GPU renderer based on NVIDIA RTX that supports both real-time ray tracing and ultra-fast path tracing. In summary, NVIDIA Omniverse is a cloud-native, multi-GPU enabled open platform for virtual collaboration and real-time photorealistic simulation. The full-stack platform based on NVIDIA RTX is a powerful culmination of NVIDIA's core graphics, compute, and AI technologies. In the next slides, Jeremy and Bengt will share with you how they are using Omniverse to enable digital twins and solve challenging problems.
From a systems and data standpoint, a true digital twin is indistinguishable from its real counterpart. At Kinetic Vision, Omniverse enables digital twins that require dynamic syncing of multiple data sources and also for managing and generating synthetic data for artificial intelligence. A huge variety of data sources can be used for digital twins. The most important thing is that your data sources will combine to represent the features needed by your downstream outputs. A photorealistic model is not always the goal. You may need to combine CAD data with simulation and physical samples to produce the right features to build a vision system that can recognize damage in a turbine blade or a package on a conveyor. The downstream possibilities of digital twins is unlimited. From quality systems to robotics design development to consumer insights, digital twins bring value to the entire supply chain and product development cycle. One of the key things we use digital twins for is to produce synthetic data to train neural networks. Synthetic data can come in a number of different forms. Any environment that can be simulated can be used to generate synthetic data. Anything from a simple spreadsheet to simulated X-ray data can be generated. You can also use GANs to create synthetic data. What is important is that your data has been validated to the real-world response. GPU technology has had a huge influence in the speed and scalability of these simulations, finally allowing the practical generation of large synthetic training data sets. We touched on the data sources, but your data is probably not as easy to integrate into a digital twin as you would hope. For example, although many companies have their own CAD data and product specs, often that data is inaccessible or not in the right format. You may have all of your product CAD data in accessible PLM systems, but your packaging artwork is stored in a completely different way or not applied to the 3D shape with the necessary UV coordinates to produce an RGB data set for training a vision algorithm. This is a huge barrier to adoption, so don't forget to plan for this critical step. The great news is that for most companies, this is usually just a data engineering effort. The technology to create digital twin assets from your data is all commonly available. It just takes expertise, effort, and some automation to scale this barrier. One big challenge is digitizing physical assets. The great news is that there are many great tools that will quickly scan physical products and turn them into digital assets. Although there are some tricks to the trade, this technology area is changing rapidly, constantly lowering the expertise barrier for scanning high-fidelity assets quickly and easily. Scalable GPU-enabled tools like Omniverse require less technical artist interaction by exchanging manual optimization and LOD creation with scalable GPU horsepower that can handle real-time ray tracing. Don't worry about decimating your models to get the lowest poly count and creating normal maps. Deploy your high-fidelity metrology scans directly into any digital twin by taking advantage of GPU acceleration. Once we've got our digital twin environment set up, it's time to put it to work. In this case, we are generating synthetic training data for an IVA model. Our AiVision framework intuitively configures data generators that quickly produce data sets for training networks. Although we still bump into a lot of experts who don't believe it works, we are generating these data sets and training highly optimized models that have never seen a shred of real data.
Synthetic data is used for training of different types of models: classification, object detection, segmentation, instant segmentation, and 6D post-estimation. Transfer learning and the use of synthetic data is key to solve many problems in the real world. By feeding back the real-world results to the synthetic data generation, the sim-to-real gap reduced to a minimum.
Now that we understand digital twins and synthetic data generation, let's talk about streaming the AI application and the important task to bring perception and intelligence to any process. I will start by design complexity. Developers need a way to leverage multiple AI models and bring them to production. Such models can be found on public repos like Model Zoo, or internally developed based on common frameworks, or leveraging NVIDIA pre-trained models. Regardless of the origin, these models need to be optimized and accelerated to run on the targeted hardware. The challenge doesn't end here. AI applications require different skill sets and teams for the different pieces of the puzzle, which in many cases translate into different tool chains during development. System software leverages the rich set of C and C++ libraries, while machine learning leverages Python. Bridging these domains is a powerful accelerator that will facilitate the creation of powerful solutions that were not possible just a few years back. The second challenge is the total cost of ownership. AI is no longer a proof of concept. It is driving new features across the board that require to deliver on an overall TCO to the end customer's user. AI products differentiate on quality, speed, and efficiency while being cost competitive. Hardware-accelerated solutions that maximize stream density is a must-have when creating an AI streaming application. And finally, deployment flexibility. AI streaming apps require the flexibility of being able to run on a wide variety of configurations that range from small ARM-based appliances all the way to the public cloud. Developers need a platform that allows them to develop once and deploy in many configurations. A platform that allows them to leverage their work from embedded to edge server systems without having to maintain different software stacks. To address those challenges, we created an end-to-end workflow, starting with our production-ready models that have been pre-trained with millions of images to achieve state-of-the-art accuracy out of the box. We offer a selection of models across various use cases from our models catalogs on NGC. Next, we have Train, Adapt, Optimize Toolkit, a training toolkit to help developers train, fine-tune, and optimize on their own dataset. Pre-trained models and transfer learning toolkits enable you to create production quality models with minimal labeled data and training iteration. You can train models without needing enormous amount of data. The models itself are not only accurate but also provide high inference throughput. And last but not least is the deployment of these models in production. For deployment, we provide powerful turnkey applications across a wide range of industries to deploy from edge to cloud using our various inference SDKs like DeepStream and Jarvis. For the objective of our presentation today, I'm going to focus on DeepStream SDK. The DeepStream SDK delivers a complete streaming analytics toolkit for AI-based multi-sensor processing, video, audio, and image understanding. DeepStream is also an integral part of NVIDIA Metropolis, the platform for building end-to-end services and solutions that transform pixel and sensor data to actionable insights. Developers can build seamless streaming pipelines for AI-based video, audio, and image analytics using DeepStream. It brings development flexibility by giving developers the option to develop in C, C++, Python, or use low-code graphical programming with Graph Composer. DeepStream ships with various hardware-accelerated plugins and extensions. It is built for both developers and enterprises and offers extensive AI model support for popular object detection and segmentation models, such as SSD, YOLO, faster RCNN, and mask RCNN. You can also integrate custom functions and libraries in DeepStream. The result is a flexible, scalable, and robust AI deep learning pipeline, empowering organizations like KION and Kinetic Vision to build powerful applications and solve challenging problems. I will let Bengt and Jeremy to share with you now how they are using the NVIDIA AI accelerated platform.
In our training data sets, we combine synthetic and real data. With this data, we train and evaluate our different models, for example, segmentation and object detection. There are two feedbacks in the process. First, how we adjust the synthetic data generation. Second, the models are used to label the real data. To get AI on our forklifts, we use transfer learning and models optimized for TensorRT, which we then deploy to our edge devices.
We also use transfer learning with synthetic training data. Most of you are probably familiar with this training process. We use the synthetic training data as our training set, and we keep a holdout set for validation during automated model training. We will also generate a test set from our digital twin that represents the real-world system. After each generation of training, we can evaluate its performance on the test set and see if we perform better or worse than the last generation. We can also incorporate conditions into our digital twin that might be very difficult to create in the real world, such as products falling over or unforeseen lighting conditions. Also, notice our use of semantic segmentation, which takes the accuracy of our labeling to a whole new level. Imagine doing pixel-level manual labeling on hundreds of hours of video. One of the great things about this approach is that you can start doing your model development well before any of your hard equipment is commissioned and get a head start on learning how your model behaves to conditions in the environment. You may even be able to influence your design, such as choosing belt contrast, lighting, or camera position to get the best performance of your physical setup. Our end-to-end solution looks like this. We use NVIDIA GPU systems for synthetic data generation, model training, and inference, combining our AiVision synthetic data generation platform with Omniverse, Tau, and DeepStream enables rapid development of deep neural networks. Finally, we use Fleet Command to manage the deployment and maintenance of these models at the edge. Now that we've discussed some of the foundations of our work, let's jump into our solutions.
In our case study, we want to tackle several of the problems in the distribution center mentioned at the beginning. Therefore, we will use a digital twin in multiple ways. Finding the optimal layout and configuration, training highly accurate AI models, developing business logic and control algorithms. In particular, we address the problems of distributing the goods from the order picker to packaging. Here, quality monitoring and throughput are equally important. For this, we will optimize the layout in the digital twin, use a physics simulation of the goods transport, and uses synthetic data to train models for product identification and anomaly detection. On this basis, we will develop control algorithms to optimally control the conveyor belts for perfect synchronization between the picking of the goods and their further processing.
When designing the distribution facility layout, we can use a digital twin of the system in Omniverse to optimize the design of the facility prior to major capital investment. Through Nucleus, disciplines that separately maintain digital models for the facility, storage, and conveyor systems can all collaborate together simultaneously to understand the best layout as the designs are dynamically coordinated as one single source of the truth. One of the advantages of building your digital twin in a real-time engine is the ability to interactively understand the physics implications of your system. Through its implementation of NVIDIA PhysX, Omniverse can simulate real-time physics. This allows for rapid screening of design parameters such as belt speed and acceleration, as well as testing many design configurations for optimal performance. As a programmable framework, Omniverse can be deployed for continuous integration testing, allowing you to automatically test any design change with a series of integration tests to increase your confidence of design performance before moving to commissioning. One of the most important activities to consider during digital twin development is physical validation. The level of validation required depends on the fidelity of the answers you're looking for. If you only need a better or worse design comparison, or you're building out data distributions of a relatively random system, then validating individual point measurements may not be as important. If your intent is to start with the first principles and squeeze the last few percentage points of performance out of an operation, then validating your digital twin becomes crucial. For our conveyor digital twin, we used product drones to validate that our twin has the same physical response as the real-world conveyor. The product drone has a miniaturized sensor package that streams data over Bluetooth while allowing beverage packages to perform exactly like they do in production, with sloshing fluid and even pressurization for carbonated beverages. And guess what? The drone sensors also need to be validated, as you can see in this video. Here we can see the response of our acceleration sensors during an offset transformation and a gate collision. We then take these measurements back to our digital twin simulation and run the same virtual test to confirm that the results match and make any necessary adjustments. One of the interesting things about doing this degree of validation measurement is that you will always discover surprises that challenge your assumptions of your design. In this case, we discovered that a section of our conveyor had uneven belt supports and in hindsight explained some unusual results we had seen during our tip stability tests. The real world is full of imperfections that may be important for understanding the performance of your system. We've also built a synthetic data generator as part of our digital twin system. With digital assets of our product data, we used AiVision and Omniverse Replicator to build out synthetic training data for training highly optimized vision algorithms using domain randomization techniques. This is a great example of why photorealism is not always the objective. Towards the end of the sequence, you can see the amount of noise that is introduced into both the background and foreground. This technique forces the neural network to learn the most important features to uniquely identify these products, despite changes in the environment. After generating around 4,000 training images, we use NVIDIA Tau and transfer learning with the pre-trained YOLO object detection architecture. We trained for about 100 epochs overnight on an NVIDIA A100 GPU. Tau has a number of different architectures to choose from, depending on your final application, the requirements, and your deployment hardware. If real-time edge inference is your goal, you may want to use a different architecture than an offline cloud pipeline. Here we show the basic data flow of our architecture. We use the AiVision configuration to generate synthetic training sets. These sets are used to train the object detection and classification model using NVIDIA Tau. Live video or synthetic video can use to evaluate the performance of our model. Monitoring our model's loss in a feedback loop drives further optimization of the synthetic training data to retrain and improve model performance. This architecture is flexible and allows for a high degree of automation, allowing the combinations of real and synthetic data to continuously optimize model performance. Now that we've optimized our model with the digital twin on the left, we can evaluate its performance in the physical environment on the right. This is incredible. Our vision algorithm has never seen a real package before. It was exclusively trained on synthetic data without coordinating a real video shoot or spending time and money on inaccurate manual labeling. When deployed on the industrial camera for real-time inference, we get fantastic results on the first test. This is all enabled by a digital-first development practice using NVIDIA frameworks. Now that we know how to train highly optimized perception models, we can revisit our distribution center and assemble solutions that address our challenges. A synthetically trained object detection and classification model confirms that we have the correct products and that we've picked them in the right order. We can also use the object detection data to tell the warehouse execution system when the conveyor is becoming congested, sending a signal to temporarily slow down the line speed to allow the picking station to catch up before we have a big mess. And finally, by deploying a pre-trained pose estimation model, we can confirm that our station is occupied and we can detect any potential safety concerns. The really cool thing is that all this data can be streamed into a data lake for broader insights into facility and business operations. Imagine being able to look at months or years of data from different lines and facilities to gain insights into what configurations create the safest environments with the most optimal throughput and lowest downtime. Now, demos are really inspiring, but anyone can do one-off experiments without considering scalability. Let's revisit some of the techniques we're using that will allow reapplication to new problems and domains. The synthetic training curriculum that we used here works well for many object detection and classification problems. All that changed here was the database of 3D assets that was fed into the synthetic data generator. It's pretty common for your environment and lighting conditions to vary for deployments. But with domain randomized training data, you can deploy the exact same model to completely different cameras that are used for unique applications. These types of training data sets are very difficult to produce manually, so not only can a digital twin framework be helpful, this will be the only way we're able to solve problems of the future. Looking at the stages of the distribution center, we can now map out several opportunities for digital twins, custom perception, and pre-trained models to make an impact. By coordinating these technologies, we can address quality across the facility. Vehicle detection, license plate reading, and OCR can streamline the receiving area, while people counting and pose estimation can make an impact across multiple stations. Digital twins and synthetically trained perception models will tackle issues with conveying, sorting, and packing. Combined, these advanced perception systems will enable the warehouse execution and management systems to be more intelligent than ever, and these types of applications are ready to start integrating today.
End-to-end perception and maintenance of quality in all operations, optimization of throughput, avoidance of downtime, and increasing of productivity is very important. The cost pressure in logistics is increasing, and at the same time the throughput has to increase as well to meet the ever-increasing transport volume. If we can first see what's going on in the warehouse, we will continue to integrate frameworks like Reopt for efficient retrieval and storage.
We've had a lot of fun presenting our work today. Let's summarize and talk about the future. In the telecommunications industry, digital twins are already common for the continuous integration testing of equipment configuration changes. Every time a significant change to the network fabric is planned, the equipment configurations are rolled out and tested first on a digital twin of the network. After the digital twin measures the impact of the changes, then those updates are certified for release to the physical infrastructure. Imagine a future where we are testing any major supply chain changes first within a dynamic system-level digital twin that runs a series of test scenarios and measures the risk of the change before deployment. Now consider leveraging optimization algorithms that will run thousands of design iterations and suggest new operational optimizations that were never possible before. The future's bright.
Let's look at the final result and operational outcome. By leveraging NVIDIA Omniverse and Metropolis, we achieved the following. Loading and unloading optimization in the receiving area. preventing of conveyor downtime, achieving resource optimization, avoiding congestion, and increasing throughput across all stations.
Zooming out to the entire supply chain, we can expect even more gains from the adoption of digital twins. Shown on the left is real-time inference solutions from NVIDIA Modulus that predict the angle of a variable coanda jet used for the galvanization process. Digital twins can also be used for optimizing the retail environment. Shopping behavior can be detected with action recognition models that are trained with synthetic data. Finally, as we think about consumer demand, advanced perception can be used for automatic reorders. Once the supply chain is fully connected, even more possibilities arise. With the advanced correlation of supply and demand to weather and economic modeling, and tracking raw materials through the entire supply chain with blockchain technology to eliminate waste. Digital twin approaches using Omniverse can make a huge impact from conveyor systems across the warehouse into the entire supply chain. I'd like to thank you all for attending our talk today. Please stick around for the Q&A session and feel free to email us with any questions. Tariq and Banked, thank you for co-presenting with me today. It's been an absolute pleasure. Please make sure to check out the rest of GTC. Here are a few other sessions that may interest you.